Welcome to the pod, Cultivating Innovation, one batch at a time. This is biomanufacturing and fermentation technology.
Welcome back to the Deep Dive, the place where we give you the shortcut to being well-informed on the crucial, often overlooked, engineering endeavors shaping modern industry.
It's great to be here.
Today we are deep diving into the world of biocatalysis. We're talking about using nature's machinery, enzymes and cells, to perform chemical transformations. But we're not staying at the lab bench.
No, absolutely not. We're following these reactions on their difficult, expensive, and absolutely critical journey from the flask to the 50,000-liter industrial reactor.
And that journey is littered with failed projects, isn't it?
It really is. We often hear these headline-grabbing announcements about a novel enzyme achieving, incredible yield in a test tube, but the commercial reality is just brutal.
So what's the core problem we're unpacking today?
The pivotal choice that industrial scientists face really right now in 2026 is this agonizingly complex one. When should they use isolated purified enzymes, what we call the cell-free route, versus using the entire living organism, the whole cell route?
And the critical realization that drives our source material in this whole discussion is that this choice is entirely non-sentimental. It is not about which is purer or more elegant.
Not at all. It's a rigorous constraint matching exercise.
Right. The question isn't which route is better. The question is, which set of industrial constraints are you best equipped to manage and, frankly, to pay for?
Exactly. The foundational driver behind all of this is pretty simple. We absolutely must replace the old guard of harsh chemical syntheses.
You mean the ones that rely on massive energy input, create huge solvent waste streams, and often use rare, toxic metal catalysts?
Those are the ones. We need to replace them with highly selective enzymatic pathways. And this translation isn't just about efficiency, it's a necessity for global compliance with sustainability goals, particularly in the really complex area of renewable carbon upgrading.
And as the sources state so clearly, successful industrial translation hinges on establishing and meeting the right key performance indicators, right KPIs.
That's a whole game.
Okay, let's unpack this. Successful translation hinges on defining the right KPIs. If we want to understand this constraint matching framework, I think we have to start by accepting industrial reality. Something will fail when you try to scale up.
Something always fails.
So we need to categorize those failure modes first.
The core decision framework is surprisingly simple in concept, though it's incredibly complex in execution. Route selection is explicitly a constraint matching exercise. You have to anticipate which specific penalty, be it cost, toxicity, a physical limit, or a regulatory burden, is going to break your process first when you scale up from liters to kilotons.
So we're really weighing two different sets of potential industrial nightmares. If you commit to the whole cell approach, you get the cell's robustness, but you risk being completely hobbled by issues like substrate permeability, product toxicity, and then managing the huge biomass waste stream that comes with it.
Correct. But if you choose the cell-free approach, you solve those biological headaches, only to be immediately confronted by a whole new set of enemies. The prohibitive cost of the isolated enzyme itself, and the extremely complex high-performance engineering you need to regenerate expensive cofactors.
That sets up the battlefield perfectly. Let's drill down into the technical trade-offs that dominate this decision matrix. Let's start with the big physical barrier that the whole cell route imposes: substrate permeability and transport.
Okay, so in the whole cell environment, every single molecule has to cross the cell wall and the cell membrane just to interact with the enzyme inside.
It has to get through the door, basically.
It has to get through the door. And if the substrate, let's say it's a highly lipophilic steroid precursor, or the resulting product, which might be a large complex molecule, if it's slow to transport or sticky,
then the internal reaction rate doesn't even matter.
It's irrelevant. The transport step itself becomes the rate-capping bottleneck for the entire process.
And if transport is the bottleneck, the economics just completely fall apart because your reactor productivity, your STY, it just tanks.
Precisely. In that scenario, the decision matrix strongly favors the cell-free route. By dealing directly with the isolated enzyme in an engineered media, often a two-phase organic aqueous system, you completely bypass that cellular transport problem.
The enzyme can just work at its own intrinsic speed.
As long as it remains stable in that, let's say, non-native media, yes, it can work at its maximum potential.
But wait a minute. If the cell membrane is such a massive hurdle, why doesn't every process that can work cell-free immediately discard the whole cell option? What benefit does that cellular container offer beyond just, free cofactor regeneration?
That is a fantastic challenge. The cell is highly favored when the intracellular environment actually helps you manage difficult chemistry.
Helps you.
Specifically, when you have a highly reactive intermediate, maybe it's a radical or a highly unstable precursor, that if you just left it floating in a crude extract or a homogeneous solution, it would immediately react with side components or just degrade.
Okay, so it's too fragile to be out in the open.
Exactly. The native compartmentation of the cell isolates that intermediate, it manages its fate, and that dramatically improves the overall purity and the yield. It's a protective function that we often don't appreciate enough.
That makes the cell less of a barrier and more of a strategic containment vessel. Now, that leads me directly to the second big constraint, which is often related to the first, toxicity. The molecules we are often trying to convert or produce are, frankly, poisons to the biological host.
And this is a really clean breakpoint in the constraint matching matrix.
Yeah.
In cases of high substrate or product toxicity, the decision decisively swings towards cell-free. If the substrate is too poisonous to allow for viable, actively metabolizing cells, you pretty much have to revert to the isolated enzyme.
Why does cell-free handle that better?
The cell-free approach lets you engineer the media. You can use higher salt concentrations, different pH ranges, or even substantial organic solvents conditions that would instantly kill a living cell, but that the isolated enzyme might tolerate for the necessary reaction time.
Can we anchor that with a concrete pharmaceutical example? That would be really helpful.
Absolutely. A highly cited case involves the chiral alcohol synthesis using ketoreductases, or KREDs. These are essential for intermediates in high-value drugs like atorvastatin.
Okay.
The precursor molecules are highly lipophilic and membrane active. They cause severe damage to the cell. Pilots conducted recently demonstrated that using isolated KREDs in optimized organic aqueous media allowed engineers to run the reaction at a really high substrate loading.
And what were the results?
They achieved 95% enantiomeric excess and really impressive space-time yields, or STY, of 2 to 5 grams per liter per hour.
That's a huge number.
It is. And furthermore, by choosing the cell-free path, they immediately eliminated the biomass waste stream. That resulted in a quantifiable 30 to 40% less process waste than the whole cell alternative would have produced.
That's a powerful, powerful argument for cell-free. But what if the toxicity is manageable, not instantly lethal? Can we keep the cost-saving benefits of the whole cell in that case?
Yes, often we can, usually through something called resting cell operation.
Resting cell.
The cell is maintained in a non-growth phase, which reduces its vulnerability and its energy demands. Crucially, the cell is still alive enough to utilize its massive pre-existing machinery to tolerate the toxic exposure for the duration of the batch, and most importantly, maintain its cofactor systems.
And that brings us to the most critical economic constraint.
The big one, cofactor cost and regeneration.
Right. This is where the whole cell route theoretically holds all the cards. Enzymes often need these high-energy cofactors, like NADPH, which are just prohibitively expensive to buy stoichiometrically.
Meaning one cofactor molecule for every one product molecule. You just can't afford that.
No way. So this is the economic heart of the cell-free decision then?
It is. If you go cell-free, the cost constraint demands that your cofactor total turnover number, your TTN, must be massive. We aren't just talking about a recycling system, we're talking about an engineered recycling system using dedicated auxiliary enzymes, often a glucose dehydrogenase or a formate dehydrogenase.
So you're building a second system just to support the first?
You are, and it's coupled with the primary enzyme, and it has to operate at maximum efficiency. You need an extremely low cofactor bleed, meaning the cofactor doesn't degrade or leach out or become chemically inactive over the entire production run.
What's the engineering challenge there? I mean, that sounds incredibly complex.
Its complexity and its robustness. You've essentially created a miniature, self-contained biological system in a tank. You need to ensure the auxiliary enzyme doesn't degrade faster than the primary enzyme, that the membrane systems, if you use membrane reactors for retention, don't foul up, and that the recycling rate is fast enough to keep up with the primary reaction's demands.
And the cost of failure is What?
The cost of failure is the cost of dumping thousands and thousands of dollars of cofactors in a single failed batch. It's catastrophic.
And if we compare that to the whole cell approach?
Oh, the whole cell is the master of cofactor regeneration. It just handles it by default. The organism provides a robust, self-regulating, high-capacity system. It dramatically reduces the engineering burden and the capital expenditure you'd need for a dedicated recycling module.
So if cofactor management is your dominant constraint,
If you need extremely high volumes of cofactor that are expensive and difficult to recycle, whole cell often provides the easiest solution. The mandelic acid hydroxylation case study using Pseudomonas crutida is a perfect example. The native cell machinery leverages its own efflux pumps and tight cofactor economy to achieve high yields without any external intervention.
that contrast is so essential. But let's circle back to what you mentioned earlier, the impurity hypothesis. If the cell is so great, you still have to deal with the cell mass itself, which is a massive source of contaminants.
And that leads us to the critical manufacturing pivot. The impurity and downstream processing, or DSP, hypothesis. Adding or changing a unit operation, especially adopting an enzymatic step, fundamentally alters the entire process impurity profile.
You're changing the recipe, so you're changing what comes out at the end.
Precisely. Industrial route choice must always be paired with a rigorous DSP hypothesis, not just a yield hypothesis. We have to ask the hard question. Will this perfect upstream yield create an absolutely impossible downstream separation problem?
So if the whole cell route gives me a 99% yield, but the biomass contaminants, the cellular proteins, lipids, and nucleic acids, have a solubility profile that makes them co-crystallize with my product.
You failed.
I've failed industrially, even with perfect yield.
Exactly. Biomass impurities are particularly insidious. They don't just reduce purity, they physically interfere with the process. Proteins can stabilize emulsions, making liquid-liquid extraction impossible. Nucleic acids can aggregate and foul up your ultrafiltration membranes. And lipids often co-partition into organic phases, contaminating the product stream.
So the goal is to choose the route whose resulting impurity matrix is the simplest to purge or separate.
That's the goal. Cell-free often reduces the impurity background dramatically by eliminating those bulk biomass contaminants, which really simplifies the initial solid-liquid separation.
This all boils down to needing a common, quantifiable language for success. So let's transition from identifying the constraints to defining the metrics themselves. How do we define good in a way that matters to the factory floor, to the CFO? What is that practical KPI set?
We begin with what I call the core feasibility triad, which every process engineer knows: titer, rate, and yield.
Right. Titer, or concentration, dictates how large the reactor must be. Rate, or speed, dictates how long the reaction takes. And yield, efficiency, dictates raw material consumption.
And while these are absolutely foundational, our informed audience knows they only tell the technical story, not the economic one.
The economic metric that captures both speed and size is STY.
Space-time yield. STY is the single most important metric capturing reactor productivity. It's measured as mass produced per volume per time, so grams per liter per hour, and it directly translates to the required reactor volume, which is a major CapEx driver.
What's a good target?
A good industrial benchmark for feasibility is generally an STY greater than 1 gram per liter per hour. Achieving the 2 to 5 GLH that we saw in those KRED pilot systems, that signals intense process efficiency, and it justifies a large capital investment.
Now let's revisit cost for the cell-free system. We need a KPI that directly measures the utility of that expensive, isolated enzyme.
That is the enzyme total turnover number, or TTN. It is the direct metric linking product output to catalyst cost. It tells us the number of product molecules produced per 1 molecule of enzyme before that enzyme must be replaced.
And for commercial viability, what are we looking for?
For large volume applications, we often require a TTM greater than 10,000. Sometimes we're pushing toward 100,000 if the enzyme itself is really costly or unstable. Failing to meet this threshold means the enzyme makeup cost will quickly dominate your entire operational expenditure.
Okay, shifting to the whole cell side. We need a metric that directly measures how well the cell mass is working, which exposes its internal struggles.
That's the biomass-specific rate. It's measured in mass of product per mass of dry cell weight per hour, GGGCW-rich. This KPI is absolutely essential because it immediately exposes those constraints we began with: transport and toxicity limits.
How so?
If your E. coli cells are operating at a low biomass specific rate, let's say well below the target of 0.5 to 1 ggDCWH for etaconic acid production, you know the issue is not the enzyme's intrinsic activity.
It's the cell itself.
It's the cell struggling to handle the inflow or outflow of materials. This forces the engineer to decide if that biological limit is a hard wall or a soft one they can engineer around.
And finally, the constraint KPI that anchors the entire endeavor in physical reality, especially in highly aerobic industrial fermentation, the ROTR margin.
The oxygen uptake rate, OAFR, versus the oxygen transfer rate, OTR. This is often the ultimate scaling constraint. It signals whether the massive hardware of the reactor, the agitators, the impellers, the spargers, can physically dissolve and distribute enough oxygen into the highly viscous, high cell density broth to meet the biological demand of the cells, the OUR.
Why is that number, that required margin of 150 to 200 millimoles of O2 per liter per hour, so incredibly high? Why is oxygen transfer so difficult at scale?
It's just the sheer physics of mass transfer and massive non-ideal reactors. I mean, think about a 50,000-liter tank. The liquid path for oxygen to travel from a tiny bubble introduced at the sparger all the way to an individual cell floating in the middle of the broth is immense.
And the broth gets thick, right?
The broth itself becomes increasingly non-Newtonian and viscous as the cell density increases. This requires immense energy input, specialized high-shear impellers, and high-pressure aeration just to keep up.
And if the OUR exceeds the OTR, even locally,
the cells enter anaerobic zones, their metabolism shifts immediately, and you get these devastating metabolic overflows like acetate or lactate, which are toxic and just destroy your yield. This KPI prevents engineers from pursuing biological targets that the CapEx budget simply cannot support.
it's like you said, you can't put a Formula One engine in a tractor chassis.
You can't.
So the KPI framework forces a continuous reality check, moving us from the technical potential of the enzyme to the physical and economic limits of the factory. That connects perfectly to the non-negotiable demands of different industry sectors.
Indeed. The KPI framework operates within the industrial quality demands, and these demands vary drastically. The regulatory constraints for a high-value injectable drug are fundamentally different from those for a high-volume industrial feedstock enzyme.
Let's start with biopharma, where consistency, traceability, and, above all, verifiable impurity control are absolutely paramount.
The process architecture here is dictated by the mandate of demonstrable control to the regulatory bodies, like the FDA. You must prove that you control every single input, and you must prove how you remove or prevent biocatalyst-related impurities, residual DNA, residual protein, cofactors from entering the final active pharmaceutical ingredient, or API.
It's a risk minimization framework.
Totally.
And how do companies satisfy the regulator that a new enzymatic route, which introduces all this biological material, is actually safe?
They rely heavily on what is called the purge and fate study logic. This is intensive analytical work providing hard evidence that even if biological impurities are created upstream, they are completely and robustly removed downstream.
And we saw this in that case study, right? The one involving the chemoenzymatic synthesis of sinagliptin-like chirolamines using omega transaminases.
Omega-Ts, yes, that's a perfect example.
So what exactly did they have to prove in that omega-TA case?
They had to prove that the final purification step, in this case, crystallization, acted as a robust purification method for the biocatalyst itself. Using highly sensitive analytical methods, likely ELISA or advanced mass spectrometry techniques that can detect trace protein, they consistently demonstrated that residual enzyme levels in the final purified API were less than 100 parts per million.
Less than 100 ppm is a tiny, tiny quantity. What's the massive commercial implication of successfully proving that purge?
Oh, the implication is massive, both financially and logistically. By demonstrating robust, consistent upstream control and purification, they could make a science and risk-based argument to the regulators that routine final batch testing for that residual enzyme was unnecessary.
And that eliminates a huge bottleneck in quality control.
Huge. It saves immense cost, and it reduces the cycle time for a batch release. It establishes good manufacturing practice, or GMP, compliance, proving that the route is not only efficient, the overall process yield in that case was 92%, but it's also controllable.
That sounds like the regulatory burden forces biopharma to favor routes that inherently produce cleaner streams, which often pushes them towards cell-free systems, despite the higher operational cost of purification and cofactor regeneration. The cost of failure is just too high.
Absolutely. The cost of a failed final batch or a rejected regulatory submission just dwarfs the operational cost of highly purifying an enzyme. And furthermore, this high level of control demands that engineers understand entirely new impurity
What do
pathways.
you mean?
When you telespape multiple enzymatic steps, or you use crude extracts containing several enzymes, you introduce side reactions. These must be rigorously mapped to controllable variables like pH, temperature, or the consistency of your cofactor module. They cannot simply be treated as noise in the system.
And the ghost in the machine is still the DSP impact. Even if the upstream yield is 99%, if the new impurity gets retained in that final crystal lattice, you've hit a wall.
That is the key conflict. A route decision that changes the chemical identity or the solubility behavior of a key impurity can drastically alter the DSP difficulty. For example, if a slightly modified enzyme variant is released during the reaction, and that variant has a similar molecular structure or solubility profile to the product, it might co-retain during crystallization.
Turning a straightforward separation into a multi-stage
A
nightmare.
catastrophic one, yes.
Let's pivot completely now and look at industrial enzymes. The high-volume stuff used in feed, detergents, or textiles. The constraints here must be volume, cost, and stability rather than ultra-high purity.
Precisely. The manufacturing reality for feed and industrial enzymes is that the final product is typically a formulated mixture. It's a product designed for function in a harsh environment, not a pristine single protein. Purity takes a backseat to sheer scale, robustness, and, critically, formulation stability.
So stability is not a quality check. It's actually a design element.
It is part of the process architecture. Consider a feed phytase enzyme, which is designed to release phosphorus from plant matter in livestock stomachs. That enzyme must first survive massive mechanical and thermal stresses, the high heat, shear, and pressure of the feed pelleting process, and then it needs prolonged storage stability in a silo before it's even used.
So if the enzyme loses 30% of its activity during pelleting, that's 30% of the entire batch cost just gone instantly.
That is the industrial reality. Therefore, stability during formulation, during drying, during storage becomes the core process design consideration. The entire route selection is focused on maximizing the formulation stability margin.
What are the primary formulation strategies used to achieve this kind of robustness at scale?
The industrially viable strategies are things like spray drying, fluid bed drying, and encapsulation. The foundational logic is to create a physical barrier. You take a highly productive enzyme, which is often produced via whole cell fermentation because of the scale and cost requirements, and then you apply a protective shell around it.
So you're building it its own little suit of armor.
You are, and the source material highlights that this proactive formulation strategy is essential because without it, activity loss during drying and pelleting is often in the 20 to 30% range. You are engineering a protective environment to mitigate inevitable mechanical and thermal stress.
It's fascinating how the entire process design just flips. Biopharma designs a process to purify the enzyme away from the impurities, while the industrial sector designs a process to protect the enzyme from the process itself.
That's a great way to put it.
Now that we've confirmed technical viability and regulatory fit, the next step in the deep dive is financial. Can we scale this profitably, and is the green story real? This requires a robust techno-economic analysis, or TEA, and a quantifiable life cycle assessment, an LCA.
Right. And a robust TA has to stress test the major financial drivers.
Where do the biggest cost levers lie in a biocatalytic route? Is it still just raw materials?
No, not usually. While feedstock cost is important, the major levers are CapEx driven primarily by reactor size, where STY is key, and DSP equipment requirements, and then OpEx, which covers utilities, enzyme makeup costs, where TTN is key, and the value you capture through cofactor recycling.
But there's a trap in there, isn't there?
There is. A critical finding from recent TAs is the dominance of what's called the purification cost trap.
Let's drill into that, the purification cost trap.
This is the observation that in industrial enzyme manufacturing, purification is frequently the single dominant cost driver. It often consumes more capital and operating budget than the upstream fermentation itself.
Wow.
The crucial insight is the exponential cost difference between crude protein and highly purified protein. For instance, fermentation might produce a crude enzyme broth costing, say, $50 per kilogram of active protein, but purifying that protein to 99.5% for a sensitive biopharma application might add another $450 to $1,000 per kilogram.
So the economic viability isn't determined by getting 90% yield upstream, but by avoiding the massive cost of getting from 90% to 99.9% purity downstream.
You've got it. This forces a rigorous internal debate. How much purity do we really need? For industrial products, accepting a lower purity crude enzyme often radically improves the economics. For biopharma, however, the choice is often made to favor a route like cell-free with integrated separation and reaction, ISPR, that reduces the downstream load even if the upfront cost of the purified enzyme is higher.
You're optimizing the total process cost by simplifying separation.
Exactly. The total cost is minimized.
That illustrates why integration is so important. The TA-relevant wins often come from smarter process architecture, not just a better catalyst.
Precisely. We see strong TEA cases where the financial benefit comes specifically from reaction separation coupling. For example, in some biocatalytic chiral amine processes, the engineers explicitly evaluated integrated membrane extraction to continuously remove a product that was inhibiting the enzyme.
And that did what?
It not only improved the rate, but it also simplified the purification, improving the overall economics significantly. You're not just substituting a chemical step, you're designing an integrated bioreactor and separator in one.
Moving to sustainability, the LCA. Biocatalysis is inherently greener because it's selective, but how do we quantify that for a defensible LCA? What are the specific quantifiable levers that improve the environmental footprint?
We have to focus on three core quantifiable benefits that shift the footprint materially. The first is the dramatic reduction of solvent use. Traditional chemical synthesis often relies on vast amounts of volatile organic solvents. Biocatalysis, running in aqueous or organic aqueous media, eliminates so much of this.
The second must be waste reduction, which often relates to those complex synthetic steps.
Correct. The reduction of waste generation, particularly the avoidance or reduction of protecting group chemistry. Protecting groups are notorious in organic synthesis for being waste-intensive. You add a group to shield one part of a molecule, you run the reaction, and then you spend several more steps and create more waste just to remove the protective group.
And biocatalysis avoids that.
The omega-TA case we discussed achieved a 50 to 70% reduction in synthetic steps compared to the traditional chemical route, largely by eliminating these wasteful protection and deprotection cycles.
And the third quantifiable lever relates directly to energy.
It's lowering energy intensity from unit operations. Biocatalytic reactions typically run at ambient or near ambient temperatures and pressures. Contrast that with traditional high-pressure hydrogenation or high-temperature pyrolysis. By reducing the need for intensive heating, cooling, aeration, and complex solvent recovery, the overall energy demand just plummets.
And how does the tactical choice batch versus continuous feed into that LCA?
Continuous processing, which is driven primarily by the need to maximize asset utilization and reduce enzyme costs, also yields significant LCA benefits. Continuous systems reduce reactor downtime and minimize the solvent and energy usage associated with batch startups and shutdowns.
So the overall environmental footprint improves because you are using your CapEx assets more efficiently.
That's it. The potential impact is massive. In hybrid routes, like producing succinic acid from Corynebacterium glutamicum, utilizing renewable feedstocks like corn stover, LCOs show 40 to 60% reductions in greenhouse gas emissions compared to petrochemical routes. That provides a clear, defensible sustainability narrative.
When we talk about the sustainable future, the focus shifts to feedstock utilization. How do we stop using crude oil and start using renewable carbon sources efficiently? The expert sources suggest this isn't about one organism doing everything, it's about engineering modularity.
That's the renewable carbon framing. The concrete industrial approach is to stop thinking about creating a product from CO2 in one mythical step and instead focus on upgrading platform molecules.
What does that mean in practice?
We take readily available renewable intermediates like glucose, lignin monomers, or bio-oils and use modular enzyme or cell systems to perform a sequence of selective transformations, each followed by an efficient separation. Modularity, selection, and separation are the keys.
And for this high-volume, low-cost feedstock processing, continuous processing readiness becomes a primary screening attribute. If you can't run continuously, you can't make money.
Exactly. When margins are thin, maximizing asset utilization is paramount. Continuous flow minimizes energy spikes and maximizes throughput. This is the industrial driver behind the massive recent investment in immobilized enzymes and packed bed reactors.
Let's connect that back to our KPI, TTN. How does immobilization directly improve the total turnover number, which is our core cost metric?
Immobilization is the technical lever that enables TTN maximization. It supports three vital outcomes: catalyst reuse, operational stability, and continuous flow. When you covalently bind an enzyme to a solid support, say a porous bead or a monolith, you prevent leaching.
So the enzyme can't wash away.
It can't wash away. Preventing leaching means the enzyme stays in the reactor, capable of performing thousands more turnovers. This pushes the measurable operational stability in TTN far beyond the 10,000 commercial benchmark, often into the high 100,000 range. It transforms the enzyme from an expensive single-use reagent into a reusable, long-life catalyst.
The evidence for these continuous packed bed systems, particularly in the renewable carbon space, must be strong to justify that CapEx investment.
It is. A major 2025 review confirmed that continuous flow in packed bed reactors achieves full conversion within extremely short residence times while maintaining stability over long campaign periods. The engineering is challenging. You have to manage pressure drop and ensure uniform flow, but the results justify the effort. Covalent immobilization is identified as the key technology preventing the failure mode of catalyst loss.
Can you elaborate on the practical example of lignin upgrading? That sounds like incredibly challenging chemistry to pull off.
Lignin is the second most abundant natural polymer. It's incredibly complex and difficult to break down chemically. But packed bed systems utilizing immobilized laccases sourced from fungi like Tramit's versicolor are being used to continuously convert lignin waste into specialty chemicals like vanillin.
And the numbers on that.
These systems have demonstrated a TTN greater than 100,000, and compared to traditional batch oxidative processes, they deliver an impressive 40% energy saving. Furthermore, the continuous flow allows for real-time removal of inhibitors, which helps maintain 70% selectivity in the conversion. It's a showcase for how continuous, cell-free routes can solve a massive chemical bottleneck while hitting both economic and sustainability KPIs.
Despite these wins, continuous systems must introduce entirely new failure modes compared to batch processing. What are the key robustness constraints here, depending on the route you choose?
The constraints become issues of time and the physical environment. If you choose the whole cell route for a continuous campaign, the system is incredibly vulnerable to contamination over time. A small microbial contaminant, like a fast-growing yeast or bacterium, can quickly overwhelm the production strain in a continuous environment.
And what else?
More subtly, the cells are vulnerable to what we call physiology drift. Over weeks of steady-state operation, even tiny changes in nutrient levels or local conditions can shift the cell's metabolic state, reducing the yield or, even worse, changing the impurity profile.
And for the high TTN, cell-free packed beds, what risks are we managing there?
The risks are primarily physical and chemical decay. Cell-free systems are still susceptible to bioburden. A slight contamination can lead to biofilm formation, causing plugging and diffusion limits within the packed bed, which raises the pressure drop dramatically. Secondly, the enzyme's intrinsic time-dependent activity loss, even with covalent immobilization, is inevitable.
So continuous readiness isn't a given.
Not at all. It requires explicit multi-month stability testing under realistic industrial stress. You cannot assume lab performance holds. You must test with variations in feed impurity, pH, and water content to confirm that the required 100,000 TTN is robustly achievable.
It's clear that in every scenario, the transition to continuous operation forces you to define and manage failure modes that were totally irrelevant in the simplified batch environment.
Exactly. We've established the matrix, the language of KPIs, the regulatory constraints, and the economic landscapes. So the capstone synthesis is applying this knowledge. Industrial feasibility is governed by whether the chosen route translates into a measurable, controllable KPI advantage once those real-world constraints are included.
Here's where it gets really interesting. Let's use the full constraint matching framework and run 4 quick simulations, 1 case study in each major sector, to see the decision hierarchy in action.
Let's do it. We'll define the target, pick the route based on the dominant constraint, set the KPI target, list the primary risks, and then propose the engineering control strategy.
Okay, let's start with biopharma.
Right.
Target purity. We need chiral amines for APIs synthesized via those omega TAs. The dominant constraint is non-negotiable, ultra-high purity, and enantiomeric excess.
Root KPIs. Okay, so the cell-free route is strongly favored here. The primary constraint is the need for exquisite selectivity and minimizing trace biological impurities. We're going to use isolated enzymes, often integrated with ISPR. The core KPI is cost efficiency through durability. So a TTN in the 3 to 10 to the 4 range. We choose cell-free because it lets us precisely control the enzyme identity and greatly reduce that impurity background.
Scale-up risk failure modes. The two major failure modes are financial and regulatory. Financially, it's the cost of enzyme turnover due to cofactor bleed. Regulatorily, it's the impurity retention and crystallization, which leads to final batch rejection.
Control strategy. We address the financial risk with engineered high-performance regeneration modules using auxiliary enzymes retained via membrane bioreactors to lock the cofactor in. We address the regulatory risk with meticulous documented purge and fate studies, confirming residual enzyme is consistently below 100 ppm via analytical validation, securing that critical GMP compliance.
A clear case where minimizing the cost of failure outweighs any operational cost savings. Okay, next, the volume sector, feed industrial.
Let's go.
Target function. High-volume phytase enzymes from Aspergillus oryzae. The dominant constraint is not purity, but survival high stability during severe manufacturing processing.
Root KPIs. This mandates a whole cell fermentation due to volume and feedstock cost, followed by processing. The core KPI is the formulation stability margin against severe pelleting stress. We're often requiring survival at 80 to 90 degrees Celsius under high shear. We chose whole cell because scale and cost dominate, and stability will be engineered after the fermentation is done.
Scale-up risks failure modes. The primary failure mode is thermal and mechanical degradation. You get activity loss during drying and pelleting, risking that 20 to 30% loss of product value.
Control strategy. The solution here lies in proactive formulation using spray drying or encapsulation. The process is tuned to mitigate that thermal and mechanical stress. This strategy allows the process to achieve quantifiable LCA wins around a 25% footprint reduction because the stable formulated product can be used more efficiently by the customer. Less activity is wasted in the supply chain.
Moving to the large-scale manufacturing of bio-based materials, biochemicals.
Okay.
Target function. Polyhydroxyalkanoates, or PHA bioplastics from Cupria vitis necator. The core function requires optimizing for high biomass content to maximize the final material yield.
Root KPIs. This requires whole cell or hybrid routes because the full metabolic pathway is needed to build and accumulate these complex polymers inside the cell. The key constraints are transport and physical limits. Our KPIs are the biomass-specific rate, targeting that high 60% biomass content, and crucially, that ROTR margin.
Scale-up risks failure modes. Transport and substrate inhibition limits, which throttle the cell's productivity, and the massive risk in high-density fed batch fermentation. Acetate overflow due to inadequate oxygen transfer or poor feeding control.
Control strategy. To address transport, genetic engineering strategies like efflux tuning can be employed to physically improve yield gains, sometimes up to 30%. To manage the physical constraint of oxygen and the metabolic failure of overflow, the control strategy requires real-time monitoring using off-gas analysis and soft sensing to check the ROTR. This allows the automated system to slow down feeding if the cells are approaching the physical limit of the reactor, maintaining optimal metabolic conditions.
Finally, the frontier of resource utilization.
Yeah.
Energy and renewable carbon.
Let's do it.
Target function. Upgrading complex lignin waste to specialty chemicals like vanillin for maximum resource utilization and continuous production.
Root KPIs. The continuous approach is non-negotiable here. This strongly favors cell-free immobilized enzymes in a packed bed reactor. The dominant constraint is the operational cost of the catalyst itself. So the KPI is operational stability, pushing TTN to be greater than 100,000.
Scale-up risk failure modes. The risks are physical failure and material loss. You have enzyme leaching from the support, which destroys the TPN and contaminates the product, and then plugging or diffusion limits within the packed bed due to particulate matter in the crude feed.
Control strategy. The defense against leaching is covalent immobilization, chemically bonding the enzyme to prevent physical loss. And robustness against fouling is ensured by explicit quality control over feed impurity variation and water content. This prevents time-dependent activity loss or physical fouling. The high TTN justifies the initial CapEx for the immobilization technology.
That was a fantastic run-through.
So what does this all mean? We've traced the evolution of biocatalysis from, a novelty in a flask to a fully disciplined, mature engineering framework. The era of simply optimizing yield is over. Industrial route selection is now purely about anticipating, defining, and controlling failure modes based on sector-specific constraints.
We saw that the core conflict between cell-free and whole cell hinges on a pivotal trade-off. Do you tolerate the engineering complexity and cost of external cofactor recycling and enzyme isolation on the cell-free side? Or do you tolerate the biological constraints of transport, toxicity, and massive biomass management on the whole cell side?
And the recurring pattern across all sectors, from sitagliptin intermediates requiring less than 100 ppm purity control to lignin upgrading requiring 10 to the 5 turnovers, is that the preferred route is the one whose dominant failure modes are monitorable and controllable with an affordable process control and downstream processing strategy. You must have a robust control strategy for the specific failure you have chosen to inherit.
We've reviewed the critical shifts. The move from single-yield optimization to multivariable constraint matching like toxicity and DSP, the adoption of truly industrial KPIs like STY, high TTN, and ROTR, and the direct linkage of these route design choices to massive sustainability levers like LCA and solvent reduction.
The entire field demonstrates that the biology, the economics, and the engineering are no longer separable entities. They are a single integrated challenge. The ability to articulate that failure hierarchy is really the hallmark of an expert process engineer.
The recurring pattern across all sectors is that industrial feasibility is governed by whether route selection translates into a measurable KPI advantage once real constraints. Impurity control, formulation stability, oxygen transfer, packed bed stability are included. What existing processes in your field could benefit most from a rigorous constraint matching exercise to expose the true scale limit? That's the question we leave you to ponder after this deep dive.
Thank you for joining us.
We'll see you next time.
How do we solve the valley of death in biomanufacturing? It starts with better data and more robust fermentation technology. Join us on Biomanufacturing and Fermentation Technology by Prasad Ornala for our upcoming series featuring lead researchers and process engineers. We're discussing everything from bioreactor design to downstream processing, DSP efficiency. Follow us now to join the conversation on the technical frontiers of biology.